I'd like to welcome to Google Ralph Simpson. Ralph is a 30-plus year veteran of technology industry, recently retired. He volunteers at History San Jose and is an avid collector of cipher machines, has probably a couple of dozen cipher machines in his collection. And he's agreed to come here today to tell us about his Enigma machine, and he's going to be demoing it and also letting people come up and play with it afterwards, I think. And,
Sure.
So welcome, Ralph.
Thank you very much, Owen. It's a real pleasure and an honor for me to be here today. I really appreciate the time that you are providing here for me. To be able to speak at a Google Tech Talk is quite an honor, and I really look forward to it. This little machine here is not only of great interest to me, I think it also reflects a huge historical value, both in terms of what it meant in World War II, as well as what it led to afterwards. Because in breaking the code during World War II, basically the Allies had to come up with modern computing. And you could argue that the computer revolution, Silicon Valley, and even Google here has its roots back to this little humble typewriter in a wooden box. And so what I'd like to do today is go through that early history, the technology of the machine, and let's see, the early history, the technology of the machine. I'll do a demonstration, as Owen mentioned, and then I want to talk about the significance of this to World War II and how the Allies actually broke the code and how that led to modern computing. Now, the key there's at the end a calculation of the key length of the Enigma, which I will not have time to go through, but it's there. It doesn't take a lot of math, and it is enlightening, so I'd encourage you to use that as an exercise for the reader. It's really quite interesting. So if you take a look at what drove the need for something like an Enigma machine, it actually started in World War I because of the proliferation of radios for the first time in warfare. And that was a huge advantage, but after the war, the Germans were horrified to find out that all of their messages were being read. And it wasn't just the Germans. Every single message was being read. And part of the reason is that if you look at the types of cipher devices that were available, they were really made for a different environment. They were made in order to send a message, a written message by courier, or in some other fashion where it wasn't on a radio. As soon as you're talking about having hundreds or thousands of messages on a radio with the same code, that can easily be broken. Letter frequency analysis, you identify which letters are the most frequent in the first letter of each message, the second letter, the third letter, and generally you can break these codes in minutes, not hours. And I brought a few examples. You see on the left here it's called a Visionaire wheel. This one was used by the Confederate Army. It was invented in the 1400s. So this has been around a long time. Here is a life-size replica of that wheel. There's only 5 in existence, so I had to get a replica. But it's a very simple device. You can see there's the alphabet in 2 wheels here. You just use a code word and spin this and come up with a new algorithm for each code word. Unfortunately, this is easily broken. And in fact, the North broke the Confederate Visionaire wheel regularly. I mean, it was, the South only used 3 different code words all during the war. So it was quite easy for them to break it. And that's despite the fact that Scientific American magazine in 1917 said this device was unbreakable. Shows you what they know. Here's another example. Now this one came out just after World War I, but it was used by the Army up through World War II. This was invented by the U.S. Army in 1922, and you can see each of these are separate wheels that have the alphabet in a different configuration around the outside. And the way it's used is you just write your message in 25 lines across this, and then you spin this wheel around and pick any other line to send as your gibberish. And then the receiver would print out that gibberish and then would have to search around the wheel to see something that looks like, normal English or German or whatever your language is. But it was also found in 1922, just by coincidence, in Thomas Jefferson's papers, that actually he invented this. I'm talking about our second president. He invented this device, and his had 36 wheels instead of 25, but he described it exactly, and they actually have an example of it at the NSA Museum in Fort Meade, Maryland, where you can take a look at it. By the way, if you have any questions, feel free to ask me as I go through this. Another thing I wanted to show you, I talked about this Visionaire wheel, and it's from the 1400s. That doesn't mean that it ended there. Here is a US version of that Visionaire wheel that was used in the Vietnam War. Vietnam. And what you do is you take this little thing down, you attach a little cassette tape to it, and then the cassette tape, by spinning this around, will put a different Morse code on the tape. You can take this off and then connect it to a radio, and it would send it in a blast mode very quickly. But it's using the Visionaire wheel. Now you may ask, why in the world would we use this in Vietnam when obviously there's much better technologies, this one can be broken? Well, in battlefield conditions, this is very fast, it's easy to do, and if you only need to confuse the enemy for an hour or two, this works. If it's more than that, it's not good. Now I wanted to show you one other, or a couple more. Another one is a simple book. This is a code book from 1988. It's called Commercial Cryptograph. There were military versions of these types of code books, but it has words and phrases written on one side, other words and numbers written on the other, and so all you have to do is just make up your message, look up the words, and send other words or other numbers, and that's how you send a code. This has also been in use since the 1400s, and this is relatively effective. The problem is, as soon as it's broken, by losing a book, you're dead in the water, and to then send out books to thousands of army locations is just untenable. So it was typically used more for diplomatic locations and high commands and things like that. And the last one I'll show you is another US Army one, just to show you what was used by the US Army in World War II to compare it to the Enigma machine. Okay, the Enigma machine is a 26-pound device. It's a typewriter. You press on a key, a light lights up. Somebody has to write it down. That somebody is usually a second operator so that they can go fast. This device is a little bit different than that. You can see there's 6 wheels. It uses a whole different technology. There's no battery, no electricity, and it's actually, it performs an XOR, exclusive OR operation in this, and then it prints out the result. And it can cipher and decipher just with the switch of a key here. So it's very handy, smaller, easier to carry, no batteries needed, but not as effective and not as cryptologically strong as the Enigma machine. So this one was used again as a battlefield cipher. It was typically broken by the Germans in a couple of hours. Okay, so let me go on. What I wanted to just show you was kind of the background of what environment was in place when the Enigma machine was invented and why there was a need for something that was stronger, that could work better than what was in existence at the time. And it turns out that the Enigma machine wasn't the only rotor-based cipher machine. Now, what was unique about the Enigma machine and these other rotor-based cipher machines is the rotor itself. Okay, this is the Enigma rotor. And as you can see, it has these little pin connectors. There's 26 of them, representing all the letters of the alphabet. On the other side is the connectors. And what it has in the middle are wires that will connect one letter to a different letter. So an A may be connected to a G in this rotor, but the A may be connected to a B in one of the others. They're all wired differently. And so this is the key innovation, which maybe doesn't sound all that great, but at the time this was huge, because when you put 3 in a row, that means that the the letter is changed 3 times. And actually in the Enigma, there's a reflector, so it goes through, and then it goes through a reflector, it's changed again, and then gets changed 3 more times. So this was quite an effective way to encipher messages. The other thing was that it made it very easy. If you notice on some of the others, it's very manual process, error-prone, a lot of fiddling around. Here, you just type on a typewriter, much less room for error. So that was the innovation. Now, it turns out that the Enigma wasn't the only one that was invented in this same time frame. Like I said, World War I showed the need, and so this was invented around the world. There are 4 different countries, 4 different inventors, all within a few years came up with this same rotor concept. And the first inventor was here in the US, Edward Hepburn. He was actually in jail for stealing a horse in 1915, and he said he came up with the idea while he was in jail. And when he got out, he came up with a really nifty-looking device. He didn't make a lot of those, although he did get $1 million worth of investment money. He built a huge manufacturing plant in Oakland that was going to house 1,500 workers. And after making a couple of dozen machines, he went bankrupt. And then he got thrown in jail again for stock manipulation. So, that one went by the wayside. Then we have the Enigma machine. Now, that Enigma machine, you can see, is different than the one that's sitting before you. That was the first version. It weighed 110 pounds, and not a lot of those sold. It was very cumbersome to use. And then by the mid-20s, he came up with this version, which is a 26-pound device, and it got accepted by the German military. Hugo Koch in Holland came up with a design. He actually developed some prototypes in the lab, but they didn't work very well. So he never really was able to sell these commercially. And Arvid Dam is an interesting guy. He came up with a device and sold some. And in fact, the guy that bought him out was named Hagelin. Hagelin formed a company called Crypto AG, and the first big sale he had was this device right here. He sold 140,000 of these to the US government, which allowed him then, after the war, to sell these around the world, or a follow-on version of that. And he ended up selling to 130 countries. Their military, diplomats, it was used everywhere. What wasn't known was that the NSA had a sweetheart deal with him and had a back door. So this story of the NSA goes way back, right? This is from the 50s, and this was that back door existed for about 40 years before it was unearthed by Iran in 1999. So there's a whole history here. I could do a whole nother tech talk on Hagelin, but I have to go on. And as you can see, on the next slide, what I want to talk about now is the Enigma machine. Now, the Enigma was invented, as you can see, by Arthur Scherbius, and Hugo Koch was the other inventor that I said never got off the ground. His device was too intermittent and didn't work well. But in 1927, Scherbius did a strange thing. He bought the rights to Koch's patent. Now, the reason I say that's strange is Scherbius had the earlier patent, and it turns out they were identical patents. So why would he buy this right? It was never really understood. It was kind of a mystery until 2003. So here, again, in the story of ciphering, a lot of times we find things out after the fact, sometimes decades or even hundreds of years after the fact. And here, what we found out was that the rotor-based cipher machine was not invented by these 4 gentlemen that I showed you earlier. We have to rewrite history. It was actually invented by 2 Dutch naval officers. They built a machine in 1915, and that machine worked. They showed it to the Dutch Navy, and this was at World War I time. They decided to squelch it, and they would not allow these 2 naval officers to patent that device. And it just so happens that the patent attorney that these Dutch naval officers hired was the brother-in-law of Hugo Koch. What a coincidence. And it turns out also that Hugo Koch and Arthur Scherbius were collaborators. So they worked together in stealing that patent and coming up with the Enigma. And I think that Scherbius felt a little bit like he owed something to Hugo Koch and gave him a little bit of money to buy out his patent. So that's the story behind Hugo Koch. So after all of this and all the stories you're going to read about Hugo Koch, it turns out it's these two Dutch naval officers that invented the Enigma machine. Yes?
Any idea who the two Dutch naval officers are?
Yeah, the question is, who are the two Dutch naval officers? I don't know a lot about them. I do know their names. It's Theo van Hengel, and the other one is RPC Stengler. Those are the two Dutch naval officers. There's not a lot of information about them, but they were the ones that invented it. They were tasked to invent it, basically, by the Dutch Navy, and when they did, the Dutch Navy didn't want it out for some reason. It's also interesting that they happened to release that requirement that they not publish this or get a patent on it, but Hugo Koch came out with his patent just 2 weeks before that release, and so it was too late. So here's a picture of it. You can see it in front of you here. This is a typewriter type device. It's the innovation is these rotors that that messes up the alphabet, and the other thing that I should mention is that the way this works is when you press a key, and this key does two things. It advances the rotors mechanically, not electrically, and it sets up a electrical signal that goes through first the plugboard, and I'll discuss each of these pieces more in just a minute. But it first goes through the plugboard, then it goes through each of the three rotors. It goes through a reflector, reflecting back through the three rotors, back to the plugboard, and then it lights up a light. So it does create quite a different algorithm, because that rotor will advance every time you push a key. And it advances odometer style, with the right one advancing once each time you press, the next one advancing every 26 times, and so forth. So that's the way this thing works. I'll go through each of the pieces here just so you have a good sense for what this is all about. I really like the way that they put this together. It's 26 pounds. It's very heavy, but this thing is definite German engineering. It's heavy duty, very well made. You can see the keys are made of stainless steel. This is over a 70-year-old device. I've done nothing to it, and it works right out of the box. And I haven't had to do anything to it other than put a little bit of oil on it, and it works to this day. And you can tell it's very it's a very strongly made because it does have to advance some pretty heavy rotors. So in other words, you can't touch type on this. You have to push down one letter at a time, and it takes a bit of effort. The other thing I should mention is you'll notice that there's only 26 keys. There's no special characters, no numbers, anything else, no space bar. So they don't allow that in the cipher message. You have to write out the numbers. You have to. They did allow an X for a sentence stop, and basically they ran all the words together because you don't want to give hints on where the spaces or the spacing of words could be. So that's the way that works. And if you go to the next element here, so I'm going to go through the way that the electrical signal will go. So next is the plugboard. Now, as you can see, the plugboard is in the same format as the typewriter keys, and the bulbs will be in the same format. It's a QWERTZ format, not a QWERTY format. And basically, what this does is you attach one letter to another. So if you were to press, for instance, here, you can see that I've got a Q, and it's attached to something. Let's call it the O. So if you press a Q here, it's going to transfer that to an O before it goes to the rotors. Okay, that's all it does. And if it comes back, if it comes back as an O, it'll change it to a Q. That's all it does. This was something that Scherbius did not design. So Scherbius designed all of this sans this plugboard. And it turns out that the plugboard added more cryptological strength than all the rest of the machine combined, which is very interesting. So the military added that, and they only used it for the military. They continue to sell a commercial version of this to other countries that did not include the Plugboard. Okay, and here's a picture of the rotors. And I think I showed you these already. One thing I don't think I mentioned was there's a little notch here. This notch can be moved to any of the 26 characters. And what that notch does is when it's in the machine, it sets the point for when the next rotor to the left will advance. Yes?
I noticed that not all the plugboard connections had connections. What happens when you don't have the letter connected?
Yeah, when it's not connected, it basically bypasses. The question is, not all the plugboard connections had a cable in it. And that was done on purpose. And so if a letter was not plugged, let's say a B, that the B just went straight through without any change. Okay, and so this is the rotors. You can see a couple of facts about these. I have 3 of them here, but in a general Army Enigma situation, they would have 5 to select from. And each day they would have to change them. And therefore, you can have 5 in one position, any of 5, 4, 3, 60 different combinations of rotors in this. You can also set this on any of 26 letters. And there's 3 of them, so it's 26 cubed. And the notch can be set on any of 26 positions, but only the right 2 rotors matter. The left rotor isn't going to move anything. So that gives you a sense for the key strength of just the rotors. It's actually not a big number. In the naval version of the Enigma, they had 4 rotors, so that gave them a little bit more, and they also could select from 8 instead of 5, so that also gave them a greater strength. Next is that I want to talk about is the reflector itself. The reflector is this item here that you see with a big red B on it, just to the left of the 3 rotors. And what that does is it takes the signal from the leftmost rotor and it swaps it for another letter. And so it works much like the plugboard, but with all the letters plugged. So if, for instance, you come in as an A and it was enciphered to a G, if you came in to this reflector with a G, it would come out enciphered as an A. And the reason for that is this allows you to encipher and decipher with the same code settings. Very handy. Ease of use was all important on a battlefield, so this made it very easy. Also, this became a very big hole in the design of the Enigma, because what it meant was no letter could encipher to itself. And so keep that in mind as I go through this, because that was a big hole. But I think the Germans felt that this was important to be able to cipher and decipher without having to change keys or change settings, and so they left it that way. All right. So here, the last section I wanted to show you on this is the lamp board. The lamp board actually has a small little light underneath each of the letters. So when you press down on a key, a light lights up. It seems very simple, but it goes through this tremendous calculation of changing letters. And the other thing I should mention is that there is a battery in this. It's a square, fairly large 4.5 volt battery that was used in World War II. I've replaced it with 2 AA batteries, which is only 3 volts, but it seems to work fine. And also, you can attach this to a 220 volt plug, which was a European power supply. And so it works with just a flip of the switch. You can attach it to that, or you can attach it to a transformer they also had. So there was multiple ways to do this. Within the lid here, you see a couple of other things. There's some spare plug cables for the plug board. There's some spare light bulbs in case you have a burnout light. Interestingly, I've had this machine for about 12 years, and I've never had a light burn out yet. Yes? To test what? Yes, hey, that's a good question. So the question is there a way to test lights rather than just trying it? Because how do you know if the light's out, right? Well, they thought of that, believe it or not. So if you look inside here, there's a little empty plug here that's written in German, but it's basically a test plug. You just put the light in there, and if it lights up, it works. If it doesn't, it's dead, and you throw it away. And so they thought of those things too. Okay. Also, I have in here a little light filter. It's really just tinted plastic. And what this is used for is when you're in direct sunlight, it's sometimes hard to see the light up. And so when you put this in here and cover the lights, it actually shows up a little bit better, and you can read these. Now I'm going to leave this in place because when we film, it turns out you can see the letters light up better even on video this way. And then here is a description of how to take care of the machine. It tells you about how to oil it, how to sand the little rotor fingers, and what you need to do to keep it operational. So here's the wiring diagram. I've already really gone through all of this, but this will just show you an example. If you hit the H key, what it goes through. And each of these numbers represents a change of characters. So if you hit the H key and the H cable is plugged over to the O, as you see, it changes. That's the first change of letters. And then it goes through the 3 rotors where it's changed. It goes through the reflector, back through the 3 rotors, and back through the plugboard. So it could be changed 9 times, 7 times, or 8 times. But at least 7 times for every hit of the key. And every time you push a key, you're going to get a different transformation. So that is the strength of the Enigma machine. So I said I wasn't going to go through the calculation of the key length of the Enigma, but I want to mention what it is. The Enigma has a theoretical maximum number of settings of 3 times 10 to the 114th. The math is at the back. You can read it. But that's far more than the number of atoms in the universe. And for this crowd, I have to say it's also 300 trillion times more than a Google. So it's quite a large number. Now, the Germans weren't able to achieve that, actually, because it would have taken rooms full of rotors and other inconveniences. So the way they used it, with just 5 rotors, the way they used the plugboard, and so forth, what they saw was 10 to the 23rd, which before the days of computers is nothing to sneeze at. Let me tell you, 10 to the 23rd is still equivalent to a 77-bit key, which, if you compare that with the original DES standard, which was used up until this century, it's much better than that. But let's compare it to what they were expecting. There were no computers. They were expecting brute force, manual type of breaking of the keys. And to break a key that has 10 to the 23rd as its key length, it would take 100,000 operators, each checking a different key every second, 24/7, for twice the age of the universe to break this machine. So I think they felt pretty safe that this was a safe machine for them. And by all rights, it should have been. But let's talk about how the Germans actually used this Enigma. First of all, they had a daily key. And the daily key, I think I've already hinted at, there were 5 rotors. They had to select 3 and put them in a specific order. That was the first set of keys. Then they had to change the notch setting for 2 of them. That is another key. They had to change the plugboard settings. Then they had to place the rotors in a particular configuration. Once they set that, they're able to send a message. But they didn't just code in a message. And the reason is, if you have hundreds or thousands of messages all going with the same key, that could easily be broken. Letter frequency analysis, again, will tell you that, what's the most frequent letter, of the first of each of these messages, the second letter in each message, and so forth. It would be quickly broken. So what they had them do was, they had them send a new rotor setting. And they were told specifically to make it random. And unfortunately, what would happen with the German operators is they got lazy. And they would just use 3 letters in a row, or 3 columns in a row, or sometimes their girlfriend's initials. In fact, one operator had a girlfriend named Syl, and the British called this type of breaking of code sillies because it was so frequent. I mean, he typically used that every day, and so we could count on him to help break codes. Now, another thing that they did was they sent that three-letter new code twice, and the reason for that was, you know, they're sending this by Morse code, by radio, and sometimes that would get garbled, and they would want to send it twice to make sure that it was received correctly. So that's what they did. They would send that twice, and it turns out that that slight problem that they created, or that slight shortcoming, was exploited by the Polish, and they were able to break the code. So now what I'd like to do is give you a demonstration of this if I can. I hope you can see enough that I can explain this to you. Okay. So like I said, the first thing you have to do is set up these rotors in a particular format. And so I've set it up. I've got it written down here, in fact, and I will put this in the message clip holder, just as the Germans would have. Okay, so this is my cheat sheet. So the rotor order is going to be 3, 1, 2 in my example. Here's rotor 1. Here's 3, and here's 1. So that's next, and then 2. And so that's going left to right. That's the order. You put this on the spindle. And you kind of press it together. And you put it in this, you put it in the machine like this. And it's in there. Now the other thing that we had to do that I will assume I've already done is set the notches in the right locations. Okay, now this is in, and I can screw this down. The next thing I have to do is put these rotors on a particular setting. And the setting that they sent me for today, and this is a daily setting, so I have to do this every day, is EJ0, EJO. So I will set this to EJO, which, by the way, all these are in numbers here. And EJO is 5, 10, and 20. And if I didn't know that, there's a little cheat sheet right here on the lid that tells me that's 5, 10, and 20. So it makes it easy and foolproof. The next thing I have to do is set the plug boards. Now, the Germans, interestingly, always use 10 cables for the plug board. And you may ask, well, why don't they use all 13 and swap all the letters? Well, it turns out 10 is better than 13, cryptologically. And in fact, the cryptologic strength goes up as you go from 0 cables up to 11. 11 gives the most, and then it drops off significantly when you go to 12 and 13. So then the question is, well, why didn't they use 11 then, if that was stronger? Or why didn't they vary the number of cables? Here's my theory, okay? This is just my own theory. My own theory is they wanted to use the same number of cables so that the cables weren't laying around extra and could get lost. And the other is, why 10 instead of 11? They felt 10 was strong enough, and it kind of matched their sensibilities of order. It's a good round number, you know? And so why not use 10? They could send that 10, it's nice and neat in their code books, and that's what they did. And so that's what they used, is 10 every time. So let's assume I've got that all set up, and now I'm an operator. I'm a German operator, I want to send a message. So the first thing I have to do is I've got it all set up to the right settings, and the first thing I do is I make up a 3-letter new setting. And being kind of a bad operator, I'm going to set it up to my wife's initials, TES. So T gives me a C. Is that right? Wait a minute, I've got this. Oh, I'm sorry. I had this on the wrong thing. 5, 10, and 15. So I'm going to type in T, and that gives me a Y. E, which gives me an H. And then S, which gives me a Y again. Okay, now I have to write these down, right? Now I'm going to do that again, because as I said, I'm typing in TES twice. So again, T, this time it gives me a Z. E gives me a C. And S, this time gives me an E. So those 6 letters I have to write down and send them along with the message. But before I encode the message, I have to set this to the TES, right? So T, if I look on my cheat sheet here, is 20. E is 5, and S is 19. So now I've set my machine to 25, 19. That's TES, and now I can send my message. And I'm just going to send a simple hello message. So I'll type in H, that gives me an X, E, which gives me an O, L gives me a D. I'm typing in L again. This time I get a Q. Notice it's different because it's a different code. And then O, which gives me an H. Now I've got my message to send. The 6 letters, which is sending the new setting twice, and then the letters of hello. The way I would send this is in groups of 5. I would send the message by Morse code across a radio usually, and then the receiver would get this message. And the message he would get would just be that string of letters that I just mentioned. And what he would do is first set this to the original code setting, which is, as I said, EJ0, 5, 10, and 15. And he would then decode the first 6 letters. And I don't know if you're keeping track, but I have it written down just in case. It starts with YHY. So if I type in Y, I get a T. H gives me an E. And Y again gives me an S. That's TES. That's what I should set it to. But I'll type in the next 3 just to verify that I didn't get some garbled message. And the next 3 were ZCE. So I'll type in a Z, and I get a T. And I'm sorry, I'm looking at this keyboard backwards, and it's a little bit different. C is an E, and the last letter was CZE. And E is an S. So it verifies. I got TES again. So now I know I need to set my settings to TES. And when I do that, that's, again, I said 20, 5, and 19. Now I can type in the rest of the message that was sent to me. And that starts with XODQH. So X gives me an H. O, oops, let me back up a minute. I didn't see it. Well, that should be, trust me, it's an E. It's just not shining up through this thing very well. XOD. I think it's, let's see, D. After telling you that this has worked flawlessly for me, it seems to be disconnecting. Okay, there it goes. Back up. 19. So it started with X. That's the H. O. Now there's something wrong here, but it worked this morning, believe me. Anyways, you type in those letters and you get HELLO. And that's how you would decipher the message. Now this seems rather convoluted. In a way it is. But comparing this to previous cipher methods, this was more foolproof. It was a much stronger cipher. And therefore, the German Navy and German Army definitely relied on this. They used this extensively. Yes?
So when they sent out the daily code, did they send it encoded with the previous day's code?
No. The question is, when they sent out the daily code, did they send it encoded with the previous code? That would be one way to do it, but what they did was they sent out a book that had 30 days worth of codes written in it. If you're in the submarine service, though, you got 3 months worth of these codes. And so there again, keep that in mind because that was one of the shortcomings of this. And by stealing the code books, you sometimes were able to decipher this. And I think if they sent it daily, it might have been a better way to do it.
If you sent it daily, you would have been able to decipher all the codes based on
Yes.
having one day's.
That's true. That's true. If you ever got one day's code, that's the other fallacy. Yeah, but the books were sent out widely to all of the Army units that had these, And there were tens of thousands of them. So that was also dangerous, you know. And sometimes the Allies did steal those code books. Yes, can I go back?
Is there a protocol for someone from books or through sending a check to report, our code book has not stolen today?
I don't know if there was a protocol because I think this was something that they did everything they could to prevent. So for instance, on a submarine, if a submarine was lost at sea or they were sinking, they were told to blow it up. Cipher machines, if the enemy were approaching and they were going to lose, they were ordered to destroy the cipher machines, the code books, everything. The code books for the boats and the submarines were made of water dissolvable type of material. So if it got in the ocean, it would dissolve. So there were a lot of precautions that were taken. And in fact, I think that led to some of the reasons why there are so few Enigma machines in existence today. A lot of those were destroyed by the Nazis as the Allies advanced on their positions. Okay, so that's the demonstration. I now want to talk about some of the shortcomings, which I've already been hinting at. You see here a picture of a Panzer General Heinz Guderian, and in the bottom left you'll see an Enigma machine. And it's interesting that there's an Enigma operator there, and beside him is the person that would typically be telling him the message to decipher and writing it down. And then the third person is the person that operates the radio and sends the Morse code back and forth. So this is quite an elaborate operation. There's 3 operators there to send a message. In fact, I would say that one of the shortcomings of this machine is that it's so strong. And so let me elaborate. This is, the cryptologic strength of this was so good that the Germans never believed that it was broken all throughout the war and afterwards. Even when they were presented with pretty strong evidence that it was broken, and they were told it was broken by their allies, the Japanese. They didn't believe it. They didn't believe that it could be broken. So that was one of the shortcomings. Another is this reflector design. I mentioned that it allows for ease of use by deciphering and enciphering with the same key, but what it also did was it made sure that no letter got encoded to itself. And one of the ways that the Allies like to break codes is come up with a crib. And a crib is what they think could be included in a message. And the Germans, being very precise in their language, and especially in the military, we could count on them to use certain words over and over in messages. And one of them was a weather report that went out to the minute every day in the morning, and the front of it said weather report. And by using those words, you can pretty well tell, you can eliminate a lot of rotor positions because you can't have one letter repeating, coming back as the same letter. So it wouldn't necessarily tell you the code, but it would tell you which ones to eliminate. So you don't have, the 10 to the 23rd key settings to try out. The other is that the rotors had a regular odometer motion to them. Now it turns out that the US, besides these 140,000 machines, which were used in the battlefield, had another machine that was more similar to this, called the Sagaba. And the difference between the Sagaba and this is that it had 10 rotors to change the letters, and it had 5 other rotors to change the motion of those 10 rotors. And it was irregular. And so by having an irregular motion, you just added immensely to the cryptologic strength. And in fact, that machine was never broken by the Germans. But anyways, the odometer movement is a problem, because what that means is you're only changing one rotor for 26 times. And then when this one flips, you go in another 26 times, only changing that same fast-moving rotor. And so the third rotor actually never moves in the entire message. And the reason is that the Germans were told never to send a message more than 250 characters. When you do, you go all over again and send a new setting. And 250 wouldn't allow that third third rotor to move. So that was one of the problems. And another is the lax operations by some of the operators, especially in the Army and the Air Force. For instance, using girlfriends' initials and things like that. Sometimes they even went so far as to send a message twice with different keys. Like they accidentally didn't reset the keys from yesterday, and then they sent the same message with today's key. That's a huge problem for anybody that understands cryptography, that you can break into a code that way. So let me ask you, see that Enigma machine in the corner? I've blown it up here. Is there anything unusual that you can tell about that Enigma machine? Can anybody spot it? It's not real obvious. Yes. What's that? Yes, exactly. It's missing a plug board. So if you look at this machine, it's actually not missing the plug board. They put some white paper or cardboard or something over the plug board. Now this was a picture taken at World War II. Why would they cover over the plug board, you may ask? What's that? Yeah, those changed every day. They changed every day. So it's not a matter of giving away a secret, I think, or not a secret of the plug board. But I have another picture of a plug board, and you can see that also has that cover. I went back and looked at a lot of different Enigma pictures from World War II that came from the Germans. And they all are either covered over or they show it at an angle that you can't see the plug board. And I think it's because this was a military edition. They felt it was a secret edition, and all the other Enigma machines went out without a plug board. In fact, they also sold these Enigma machines to the Italians and the Japanese, sans the plug board. Yes, question?
Sure, it wasn't just a wrist strap.
The question is, am I sure it's not a wrist strap? Well, if you put this up, it doesn't really provide much of a wrist rest there, because you've got the wooden board here anyways. And on top of that, you're not touch typing. You have to push down pretty hard on these things. So I thought that was interesting, that they felt that this plug board was important enough that they kept it covered in the pictures. Yes?
So a machine without a plug board would not be able to decode a message from a machine with a plug board?
That's right. Yes, exactly. So the question is, if it didn't have a plug board, you couldn't decode a message from a machine with a plug board, and that's true, because that adds a whole different level. Unless you took out all the plugs, then it would be equivalent. Okay, so let's talk about how the Allies actually broke the Enigma code. It was broken by the Polish, and I'm sure all of you have heard the story. This seemed to be a little bit kept secret, not secret, but people thought that the British are the ones that broke it, but actually the Polish did. And what happened was in 1932, being between Germany and Russia, they were very nervous about the military buildup of these large countries on their borders. And so they were carefully looking at the messages that the Germans were sending, and they noticed a difference in 1932. And that difference was, it looked like these were not being coded with the same cipher machines that they were using, or the cipher devices they were using in the past, and it was some kind of machine cipher. They eventually were able to reverse engineer an Enigma machine. They figured that out through the commercial Enigma and saw that they also had some kind of other swap like the plug board, and so they reverse engineered it. And also the Polish did something else. They, for the first time in a cipher bureau, they hired mathematicians. And Marian Rejewski was the main mathematician that they hired, who ended up breaking the code. And it turns out that they actually could not break the code, even with this. First of all, they only had 3 people working on this in Poland. Okay, 3 mathematicians. But in 1933, it turns out that the French approached an official in the Cipher Bureau by the name of Hans Thilo Schmidt. He got that position because he's the brother of a decorated Panzer general. And but this particular person was in debt. He needed money, he spent a lot of money on wine, women, and song. And as they say, he wasted the rest. But since he was in need of money, he went to the French and offered the Enigma codes, the keys, and some diagrams of the Enigma. And so the French took it, gave it to the Poles and to the English, and the French and English could not break the code even with those keys. Now, they could break the codes for those days, but it didn't help them break it afterward. The Poles took that information, got the information about the double coding of the day's keys, the three-letter setting. They were able to figure out that if you type TES twice, the T and the T, if the second rotor hasn't moved, gives you a hint. And the E and the E and the S and S. You don't know what the letters they are, but you know that they're the same. And so that gives you a hint if you had the rotor wiring and the reflector wiring to help figure this out. And they were able to figure it out. It's maybe not quite as simple as I described. It still took quite a while, but they were able to figure that out in 1933, early 33. They had broken the code and were reading it until 1939 when they got invaded. And the day they got invaded, September 1, 39, is the first day of World War II. So they were successful in this. It turns out that in July of 39, they finally told their allies, the French, who had given them the way to break it, and the English. And both the French and English were astonished that they'd been breaking this code for 6.5 years, and they had not themselves made any progress. And in fact, besides breaking it, the Poles made what they call a bomba. It was a device that strung together 6 Enigma machines and allowed them to break the code much faster. They were able to break the code typically in about 15 minutes every day, and then the rest of the day they would decode them in real time, just as fast as the Germans were decoding them. And so this was quite a breakthrough. They passed this along, and unfortunately for them, they passed along replica machines, all the information they had, and then very quickly afterwards, the Germans invaded Poland, and it was all over for them. And so the UK set up a major operation to help break this code. Here's their park. They bought this home in Bleckley Park, north of London. They had up to 11,000 people working on this. Remember, the Poles had 3. So, but to their credit, they had a much tougher problem to solve. When the Poles had to solve this problem, there were only 3 rotors. And so the 3 rotors were in different positions, of which there's only 6. That's why their 6-machine bomb worked. But now that there's 5 rotors to pick from, now all of a sudden you need 60. They didn't have the ability to create a bomb with 60 rotors. And so they left it to the English. Now the English also could have done a 60-rotor bomb, but that would have been quite an undertaking. They figured out they could do a 36 Enigma bomb and manually eliminate some of the settings and still figure out the code fast enough. So that's what they did. They made a 36 machine bomb, and they were able to break the code, typically in a few hours, because what it would do is it would allow the operator to know which settings could work. Then they'd have to manually test that setting and then go on and test the next one. Also, interestingly, throughout the war, the British were very careful with this information. So if they got information that said, for instance, that a submarine was going to surface at a certain location to be resupplied by a mothership, they wouldn't just go and bomb that location, because then it would give away that they had read this message. So what they would do is they would fly a spotter plane over it to make sure the Germans saw it. Then their boat that happened to be nearby would come over and bomb it and blow it up. This almost backfired on them once. They knew that there were going to be 2 submarines being resupplied in this remote location in the Atlantic. So they sent out this spotter plane, they bombed it. But in that same exact message, it said that there were going to be these other submarines going through this strait in northern Europe. And they had to decide which ones they wanted to bomb. They decided to get the ones in the mid-Atlantic. Well, it turns out that legitimately the Allies found these submarines going through this strait, and they knocked one of them out. And so this caused a big concern by the British military, and in fact Hitler called a meeting that included, the Navy, the Air Force, and the Army, and all of the heads of these groups came in to discuss, the possibility that the Allies had broken the code. But they also brought in the person that was in charge of the Enigma machine, who told them why it was absolutely impossible for them to have broken this code. And so they all went on their merry way and nothing was done. They could have easily started changing things, but they didn't even do that. So let me set what was going on in the North Atlantic with the U-boats. Before the U.S. entered the war, the U-boats were having a field day. They were sinking Allied boats in droves. In the few months before the U.S. entered the war, it was 60 boats per month, at a tremendous loss of life and loss of supplies that were really needed for the war effort for the Allies. The U-boats, and the way they would do this is they would form wolf packs. There would be a number of U-boats all roaming around the Atlantic. They would spot a convoy because they were all separated. But rather than attack it with one U-boat, they would send a message back to headquarters. Headquarters would then say, form a wolf pack. Here's the location. Maybe up to a dozen U-boats would go there, and they'd all pick out a different boat, and they'd fire on them simultaneously. And it was at a tremendous loss of life for the Allies. And this went on for many months. So it turns out that this was a major strategy of Hitler's. He was expecting that the UK would capitulate and surrender because of this blockade and the lack of supplies. And you can see the quote here from Winston Churchill. He said, "The only thing that ever really frightened me during the war was the U-boat peril." Now this is despite the V2 peril, the peril of D-Day and the landing there, all the problems they had in Africa. The U-boat peril was the only thing that really frightened him, and I think for good reason. I mean, this could have lost the war for him. So here's what changed that. U-110. You've probably heard about the movie or seen the movie U-571. That was an important U-boat that was captured, code keys and all that. But this was the first one, the U-110. And here you see the captain. He was actually a hero in this. The U-boat was purposely captured in a way that they wanted to get the code keys from the U-boat. And so when it was bombed and it surfaced, rather than just let everybody surrender, if they did, they would have scuttled the U-boat. They would have set off charges within it, and it would have sank. So they purposely started shooting at the tower to get everybody out of the boat quickly before they could set these depth charges. And they did. And by getting everybody out quickly, they then rounded them up and put them on the Allies' boat, this HMS Bulldog. And the captain saw what was happening, and he saw that the charges were not set. So he jumped in the water to swim back to set the charges to sink his boat. And the Allies saw that and killed him. And so the Allies went on board, got all the Enigma machines, all the code books, and this boat happened to have been out for about 1 month. As I said, they have 3 months worth of code settings, so the Allies now had the next 2 months of code settings that they could break very easily, and that's exactly what they did. This single act is what changed the Battle of the Atlantic, and the reason was not only did they have the next 2 months, it gave them insights into the kinds of messages the Germans were sending, the kinds of cribs they could look for, and how they could then break future Enigma codes from the Navy. So here's how this goes back to the beginning of computing. And the father of computing is considered Alan Turing. Hello? So, okay, so here's Alan Turing. He was the person that led the effort in the UK in breaking the code. He was a mathematician who came up with, he was the brains behind, breaking the code. And he came up with the English version of the bomb. By the way, the bomb was named after, they think, an ice cream treat that the Polish code breakers were eating at the time they came up with the idea. But others say it could be the ticking of a bomb. So we're not really sure. In the UK, they built 210 of these things. Now these, as you can see, they're not insignificant. They're quite large. The one you're looking at here is the US version of the bomb. The English version had a column of 3 Enigma rotors, and it simulated 36 machines. These rotors on the English version would spin about twice a second, so quite fast, but slow enough that when they got a possible hit, it could just stop. The operator would then write down that setting for someone to manually test out to see if that could be a possible setting. Meanwhile, they would start back the machine and it would spin again. Now, all of that would not have worked for the naval Enigma. And the reason is there's just not enough hours in the day to do this. The naval Enigma, having 4 rotors selected from 8, it's hugely more difficult to break. They also had a selection of reflectors that I didn't mention that were pluggable, so they could change the reflector. So it was immensely more complex. And so what the US did was they invented a new kind of bomb. Not only did it have 4 rotors and it spun faster, it spun at a rate of 29 revolutions per second. So the problem with that is, well, first of all, the problem is the brushes wore out quickly, and it was tough to manage. But the other problem was you couldn't stop it and then read the setting. It was spinning too fast to stop it on a dime like that when it's going 29 times per second. So what they did was they came up with a new invention. And that invention is memory. Believe it or not. So the top of that machine, that box that you see on top, that long box, that is memory for 4 bytes of information. And you can see this machine at the NSA Cipher Museum in Maryland. That top box held radio tubes. Each radio tube represented a bit of information. And it held the 4 bytes that represented the code here of the rotor code. And it would print it out. So this was a major advance. And I would almost say it's memory, right? So it's the beginning of modern computing. The British also came up with another machine to break a different type of cipher device, which was the cipher device they used for telegraphs. And that was called Colossus. And that also was another step forward in modern computing, and because it was programmable. Okay, so this is the beginning of computing. This is what we're talking about here, as far as this homely little wooden box that looks like a typewriter set the stage for things like computing and Silicon Valley and Google and all of that. So by the end of the war, the US was able to break the naval Enigma code in 12 hours. That's quite a while, but from then on, they were broken in real time. So that was quite an advantage that they had. They were able to identify where these submarines were. They were able to blast them out of the water, and it turned the tide. This turned the tide of the Battle of the Atlantic. It was unfortunate that by finding out where they were, they had to select which convoys they were going to save. They could not save them all. That would just give away the entire secret, and then they would be out, that information. So they would have to selectively pick which ones they wanted to take care of. Another way that they were able to break these codes that they found out was that the weather trawlers, these were almost unarmed small boats that they could easily capture, and they would have 3 months worth of Enigma codes on them. And they would purposely, of course, sink them immediately and make sure that the Germans never suspected that they were really after them to get the code books. So what happened by the end of the war was that 82% of the sailors that went into service, including the admiral's son, Admiral Donitz, who was in charge of all these, his son was one of them, died at sea. And 725 of 1,155 U-boats were gone. And in fact, toward the end of the war, even before the end of the war, they quit going out into the Atlantic altogether. It just was not fruitful for them. They were losing more submarines than they were sinking boats. One of the things that you'll read, if you read up on the Enigma, a lot of people will claim that breaking the Enigma allowed the Allies to shorten the war by about 2 years. That's a made-up number. I don't know if it's true. But 2 years would definitely have saved millions and millions of lives. I think there is no doubt that whether it's 2 years, 3 years, 1 year, it made a change and a huge difference in the war. But even, I think, greater than that was breaking it allowed the invention of the modern computing, which has changed our lives forever. And I think that's, that is the legacy of this device. Now, after World War II, it's also interesting that a couple of things happened. One was nothing happened. So here we have this huge success. There were 11,000 people working on breaking this code in the UK, and there were several thousand in the US. And nobody told this secret. I can't imagine this happening today in the day of Snowden and releases and all that kind of stuff, but this was kept secret for 30 years, until 1974. So in the meantime, there were some of these Enigma machines around, some of them without the plug boards. And the US and the UK encouraged our allies to use these things. And our allies and enemies alike used them for 30 years. And unbeknownst to them, they were being cracked. And this particular machine came from Norway, one of our allies. They were invaded early on in World War II. The Germans left behind these machines because when they left, they didn't have time to destroy all the things they left behind in Norway. So Norway's secret police, their equivalent of the CIA, used these machines for 30 years, with the US and Britain decoding every one of those messages. So in 1974, when this was disclosed, they made these things surplus. And as a result, it went on the surplus market and eventually into my hands. The other thing I should mention is kind of the rarity. Some people ask me, how many of these were made? How much are they worth? Those kind of things. We think about 30,000 of these machines with the plug boards were made. We found serial numbers up into the 28,000, so we're assuming around 30,000 were made. Today, we know of about 350 that exist. Half of those are in museums, half are in private hands, and of those half that are in private hands, about half of them are in the U.S. So the U.S. has the majority, half of them. The rest are scattered around the rest of the world. And these things have been quite collectible. Around the year 2000, you could pick these things up for $20,000 or less, and they stayed that way for quite a few years. I picked this up in 2002 for less than $20,000. But today, they seem to be going for over $200,000. I know of, the highest that I know of one selling for was $260,000. But oftentimes they're going on Sotheby's or Christie's or something like that, and they're bringing $200,000. I think partially because of the added notoriety, because of a couple of movies that have come out. One is called Enigma, one's called U-571, which depicts a U.S. crew boarding a submarine and stealing the codes. It's actually a British crew that did this, so the British aren't too happy with our movie. But that's what's happened. And I call this a collector's item for the uber geek. So I consider myself an uber geek for having such a thing. If you're interested in downloading this presentation, I have it on my website. My website is ciphermachines.com. You can just type that in, enigma.ppt, and you can download this entire presentation, including the follow-on addendum that has the mathematical calculation for the key, for the length of the key. So, are there any other questions? Yes?
What's the actual origin of the word Enigma?
I don't know the actual, some people have asked me because they think, did the US or the British use this word and the Germans did not. It turns out Enigma means the same thing in German as it does in English, and it's spelled the same way. Now, I don't know if that's part of the reason that Sherby has picked that name, but Enigma is, it means the same thing. It's a puzzle, a tough puzzle to break or something like that. And it's identical in both languages and spelled the same way. So maybe that's just fortunate, I don't know. But I'm not sure of the original origin of the name. Yes, other questions? Comments? Yes?
I know that people have published the way that it works. I know that people have designed replicas based on Arduino.
Yes.
Has anybody actually published engineering diagrams of the actual mechanics of the machine?
So the question is, has anybody published engineering diagrams of the mechanics of the machine? I believe they have. Now, I haven't really looked for that, so I can't say for sure, but I believe they have. I think that if you look online, I think you'll find quite a bit. I know of a person in North Carolina who actually makes these replicas to be almost as precise as could be, other than they look new. So when he builds it, you can't tell the difference other than it looks new. And I mean, he uses the same crinkle paint, the same exact materials, and I believe he goes to Germany to get the same trees to make the wood. So it's quite precise. Yes, and actually, one of the things that surprised me when I received this machine was it's in relatively good condition. If you take a look afterwards, you're welcome to come up and take a look. The paint looks good. It's hard to believe that it was made in 1941. It's over 70 years old. Went through the war and afterwards, and it still looks in relatively good condition. I think that these were pretty well babied by their operators. I think they understood the value of it. They knew that they were to value this with their life, that if an enemy came along, they were to destroy it, and therefore they took very good care of them. Although on the outside of the box, you can see that there is quite a bit of, oops. Oh, I've got something blocking it here. There's some scratches and so forth. But for a 70-year-old device, I would say that's in relatively good shape, for going through the war. I can imagine this thing got quite a bit of use during that time. Yes?
Any theories why Navy switched to better ones, but the Army and Air Force didn't?
Okay, the question is, why did the Navy switch to a better one and the Army and Air Force didn't? I think it has to do, and this is my theory, I think it has to do with Admiral Dunitz. He was skeptical that this had not been broken because he was not, he trusted his submarine operators, commanders, to be able to do what was needed to fight the war, and they were losing. And there were enough evidence that he thought that this could be broken. On the other hand, it could have been spies. It could have been other technologies like radio direction finders or something like that. But I think he was suspicious all along. And so part of the way, along the way, he came up and had them design the floor rotor. The Army and Navy decided they didn't want to go with that because it would have been quite a bit more work for them to then swap out all these machines. And remember, there could have been 30,000 of these, to swap those out in that many locations versus a few submarines and a few boats. It was easier for the Navy to do that. I think it was a combination of things like that. In fact, they interviewed Admiral Dunitz after the war and asked him if he thought that the code was broken, and he said no way. And then in '74, when it was announced that it was, just before his death, he was quite surprised. So that I think even though he was suspicious, he still believed that it was safe. Yes?
So how much more complex would it have had to be for them to have not been able to do it in 12 hours, let's say 36 hours for the rig code in the day?
Yeah.
How much more complicated would they have had to make it so that it would have
Okay, so the question is, how much more complex would the device have to be that it couldn't be broken in 12 hours? You know, just adding, not even adding another rotor to the design, but adding a couple more rotors to what can be selected from would probably do that, and more. You know, that adds a lot of complexity when you have these extra rotors. And if you're only supplying a few to some boats and some submarines, you could probably do that. I don't think they felt it was necessary, you know, and so why didn't they do it? They had no suspicion that this was broken because of the care that was taken to make sure that you know, that they didn't misuse the information. Or the British didn't even tell their commanders many times where this was coming from. They would tell them this came from a trusted spy, and so they would act on the information, but not you know, even know that it came from breaking the Enigma code. Yes? I think we're out of time. Okay, we're out of time. Yeah, feel free to come and take a look at the machine. I thank you very much for your time and attention.